A number of you have asked me about the final exam issues with that, or how to study for it. So let me take a few seconds to talk about it. Final exam will be 60 multiple choice questions. So it will be superficially just like the midterms, except twice as long. You have most of you 180 minutes to work on it, which is more than twice as long as you had to work on the midterms. So if history is any guide, there's no one here after 3 hours. It's way more than enough time. If you're here, you either came late because you overslept, or you're turning right answers into wrong answers. A way to think about the final exam is it's 2 midterm exams, shuffled together. Sorry, it's two exams of 30 questions each, shuffled together. One of those halves is the third midterm, covering material since the second midterm. And the other half of the exam is open season on anything. So that's sort of how I try to pick out the questions, is so I cover the last third of the semester with 30 of them, and then the other 30 are anywhere. It's approximate. To study for them, I do encourage you, as usual, to take the old exams. Again, don't look at the answers, take them, because the thinking is important. The process of suffering over trying to find the right answer, trying to identify the wrong answers. Realize that once you find the right answer, assuming I've written the question properly, once you find the right answer, the other 3 answers must be wrong. Or if you find 3 wrong answers, the other answer must be right. On extremely rare occasions, I mess up and I have a question that has a right answer and a not so right answer, one that's not truly wrong, but I aim to make the wrong answers just wrong. Okay, so be aware that we cover different material each year, so that this year I think I actually have covered less material than in many years. So you will find questions, for example, on how metals, the materials work, metals, glass, plastics, rubber. We haven't done that. You may find stuff on medical x-ray stuff that we haven't done either. But so be aware that you may encounter questions that are, where did this come from? We didn't do this semester. What else? A value to the questions, apart from you possibly seeing those questions. And also, you're welcome to go back to the old the other midterms too. They're all useful, and I gather ideas from all of them myself, including our midterms, 1 and 2. You will probably see questions on the final exam repeated from the midterm. You saw that in the second midterm. I repeated questions from the first midterm. That may happen again. What else here? Even if I don't ask you a specific question, a value from the old exams is they give you some idea of what I care about. What are sort of the high points of the content, as opposed to the details or things that I don't really expect you to ever have retained. These will show you things that I hope that you have learned and will retain. Questions, other things? Nothing else is popping into my head. You okay with the idea of midterm? The final, it is May 7th, Monday at 9 o'clock. It'll be Scantron based, the usual, the bubble sheet forms. I guess they're not called Scantrons anymore. And anyway, I do it myself, so it's unofficial altogether. Okay? And I will keep holding office hours until, well, I won't have them Monday afternoon, but that'll be the last time. So during the finals week, that Wednesday, I'll have morning office hours as usual, that sort of thing. All right? So back to content. I do want to, on Friday, get to nuclear weapons, because it's something you ought to know something about. So I'm going to blast through optical communication, recording, and audio players, and hit what I consider the high points of those, things that you ought to know. And I talked toward the end of last time, or at the end of last time, about the difference between analog representation and digital representation, and I will rehash that briefly. When you're trying to represent something, so in effect you're representing, you're sucking out the information content of something, sound, video, a table of everybody's phone numbers. When you're trying to represent those pieces of information, you can do it as via analog means or digital means. Analog means that you're taking something, typically a single physical quantity, like the air pressure in this room, or there are variations in air pressure about the average, which is to say sound. Fluctuations around average air pressure, that is sound. If you're trying to represent that one physical quantity, you represent it using one other physical quantity, like the current in a wire, the intensity of a radio wave, the level of my hand above the floor. And that's analog representation. It's very simple to do, in concept at least. The problem is it's very susceptible to noise issues, and noise is a sort of a catch-all for any sort of thing that messes up your ability, in this case, to observe or measure the representing physical quantity, how high my hand is above the floor. In principle, I can represent exquisite detail in the air pressure in this room by exactly how high my hand is above the floor. The problem comes in how are you going to measure that? It's not easy. Do you actually care about the difference between this and this? You're going to have to get a microscope out and see the difference. And the other thing is, suppose that there are a herd of, again, birds. I'll send birds through, and you're trying to figure out how high my hand is. And in the midst of all this stuff going on, it's hard. There's an earthquake. My hand's bouncing up. Now, the floor is bouncing up and down, but how are you going to figure out which is which and stuff? So analog representation is inherently susceptible to noise. You can get exquisite detail, 4D digits of decimal information about what the air pressure is, but you're never going to be able to observe it. I can represent it all I like. You won't be able to figure out. You can maybe get a couple of useful digits of information. In contrast, digital representation uses a stream of, they could be called digits, but instead, more generally, I'll call them symbols. And now you can get all the detail you want. If you want to represent the air pressure measurement, about the fluctuation about ambient air pressure right now, measure the pressure right now to exquisite detail and represent it as a series of symbols, like decimal digits. Symbols like, there's 1. It's a 3. So the first digit of the air pressure measurement might be a 3. The second digit might be a 6. Third digit might be 9. Okay, I didn't have to go. As long as the person observing these symbols can distinguish them from each other through all a rainstorm, the world bouncing up and down, as long as you can figure it out, there's no information lost, exactly none. And so it takes a lot of symbols, and each symbol might be a physical quantity. So I could do it like if I choose just 2 symbols, I'm going to work with a set of symbols, and I'm going to work with a set of only 2. This is a 1, and this is a 0. And I go, you can distinguish those perfectly, right? And even if we dimmed the lights and messed up the room, you can still tell this from this. So I can give you a series of symbols, 0s and 1s and 0s. And with 0s and 1s is the simplest collection of symbols you could ever imagine. It's the binary collection of symbols. You can represent as much information as you like. It's not unrelated to Morse code, a series of dashes and dots, or smoke signals, series of puffs or no puffs. They're all symbols that convey information with no loss. So you okay with that idea? If you've ever read The Count of Monte Cristo, there's a part of the plot late in the book hinges on the use of the French semaphore system. To convey information across France, they would use these semaphores, towers separated by vast distances, and they'd be staring at each other with telescopes. And the towers would have arms, veins that would do these various motions. You've seen people doing this at guiding airplanes in and stuff, or maybe. So the semaphores would convey information as a series of symbols with no loss. Okay, it's not like, yeah, it's no loss. All right, so all the digital transactions you ever deal with, and digital recording, digital computers, they're all working with symbols internally. Those symbols might be currents and wires, or the amount of charge on a capacitor, things like that. But it's the same concept, just repeated over and over. So that's digital. So if you want to store music or video using digital representations of the information on disks, well, one of the ways you can get the most information on a disk, and you can make it in a way that you can mass produce it, is with CDs, DVDs, and Blu-ray disks. And the way the information is represented on those disks is as patterns of reflective patterns in a reflective surface, or actually multiple reflective surfaces. So if you look at a CD, it's got this exquisitely thin layer of aluminum in there. It's thin enough you can see through it if the light behind is bright. And it is not flat. It has all these, depending on which surface you look from, it's either divots or dimples. And those are symbols. They're representing digital information. And that's sort of enough to know about it, except the writing process involves lasers, but you're more aware of the reading process, although, you're more aware of the reading process. Again, it uses lasers. Why lasers? Well, because the lasers can be focused onto these little details and consequently observe them. And they're focused with lenses the way you're used to seeing. You send the light. The light from a laser can approximately be thought of as you can think, if you think of it in terms of rays, it is in fact a giant wave, which we'll come to. But if you think in terms of rays, you can think of it as coming from enormous distance. So the rays are all traveling the same direction, and hence they travel these from a laser pointer here to the wall without any significant spread. The rays are just keep going straight. That's a little oversimplified as we'll see, but the idea is okay. And if you take those rays into a converging lens, they begin to bend toward each other and they meet up somewhere. And because it's a single wave, all the photons are the same, they meet up all together and they make one really bright spot. It's not a point in light, point in space. It's a small, what's called a beam waste. I'll show you that in a second, because of the wave nature of light. But you can really put the light on one of those little features in a CD or a DVD or a Blu-ray, and therefore see whether, what it looks like in effect. You don't really need the full detail. Mostly they want to know how long the feature is or whether it's there. And that's the symbol representing the information. All right? Why, CD, DVD, Blu-ray, what's going on in the evolution of those? CDs showed up in the 80s, or maybe in 1980, give or take. DVDs were later, and Blu-rays are in the past, 10 years or something like that. What's the issue here? The reading process, just to give you a very brief story of it, the reading process consists of starting with a laser. It's actually a laser diode. We've seen those before. They're using the characteristic of a diode to the electrons dropping from conduction levels to valence levels, emitting light. They allow it to amplify its own light. They put it in a cavity, basically, of mirrors, and they allow it to amplify its light. So you get a giant wave coming out of this thing. And the wave, as we'll see, well, I won't go. Why does it spread initially? It spreads initially because it's coming from a small opening. And waves coming from small openings have to spread. We'll come to that in a minute. It's called diffraction. But anyway, the wave comes out, it's focused, it's played with, it's focused to a tiny spot on that symbol feature, the symbol surface within the disk. It instantly goes, the spot is bigger when it enters the plastic, which is why these things are relatively insensitive to dirt and crud on the surface. The spot of light is big, it can go around the crud. Even a little crud doesn't cause trouble. A lot of crud does, of course, but they're relatively insensitive to the dirt. The the rays all meet up at one spot inside the plastic on the surface of the shiny symbol layer. And it reflects back, and then they observe that light coming back with a diode that is sensitive to light. When light hits the diode, the photons move charges from the valence level to the conduction level. They put the energy back in, and suddenly the diode is able to carry electric current, actually in this context, backwards, opposite the direction it normally carries current. The light actually sort of opens the door for charge to go backwards. Anyway, the point is that you're using a laser to observe that surface. So is that okay so far? Well, why can't you make the symbols on the surface smaller and smaller and put more and more information so you can like put the whole, all the seasons of orange is the new black on a single disk, okay? Why can't you do that? Well, because they'd probably get you for copyright violation. But apart from that, you can't do it because there's a limit to how small you can make the symbols and still observe them with a laser, and it depends on the frequency and therefore wavelength of the laser. It's due to a phenomenon known as diffraction. When you take a laser beam, so here's my picture of a laser beam, it's traveling along, and you put it into a converging lens, and you're trying to bring you can think of rays initially, trying to bring the rays together. The rays in principle should meet up at a point in space of no size at all. And that would be great. You can now project all the light from the laser beam onto a symbol as tiny as you like, 1 atom, for example, or half an atom, okay? But that doesn't actually happen. Why? Because now you're working with, when you get things very small, when in fact the wave nature of light becomes really important. You're actually dealing not with rays, although rays are a nice approximation when you're working on a large scale. You're actually working with a wave, and you're trying to get the ripples in this wave to become narrower and narrower and narrower until they're really tiny, and they will not get much smaller than the wavelength of light. You have a tough time forming a spot. It's called a beam waist here because it doesn't actually get to a point. It gets to a waist, like the waist in an hourglass. I'm thinking of Wizard of Oz, the famous hourglass, which he throws on that waist gets to a certain width, and that's it. The size of that waist, it has a little to do with how, well, in fact, a lot to do with how big the beam was when it went through the lens. Because how big the beam was when it went through the lens and the wavelength of the light. Why? Because to put all the light wave into this tiny spot, you need to use constructive interference to build the wave intensity up in that narrow spot and kill it off outside. Just use destructive interference to kill it off everywhere else. Right now, when I'm sending this laser beam on the wall, the spot is small, despite the fact I'm sending a wave across the room, and the spot is small because all the pieces of the wave that leave the output of my laser pointer, you can think of them, all these parts of the wave, they're all working together to cause constructive interference on beam center and destructive interference everywhere else. And I mean, that may seem like an unnecessary way of thinking about it, but it turns out to be important. Because if you start killing off parts of the wave by blocking them with something, then it has trouble getting the constructive interference it needs on center to be bright and the destructive interference off center to be dark. You've hobbled it. You can't do that. And I can show you this effect. So here we've got a fancier laser, really, and I'm going to send it through pinholes. This is apropos of your problem set. I'm going to dim the lights. Don't fall asleep. Let me go through this is a very small hole. Let me go through a big hole first. It's down here, let's see. I'm going to go. So now I'm letting the laser beam go almost unobstructed. That's the whole laser beam, tiny spot, excellent constructive interference on center, and excellent destructive interference off center. But if I start truncating the wave by blocking parts of it, here's half the diameter of the hole. It's having a little, not noticeably yet, it's having a little more trouble building the bright spot and putting dark around it. Here, more trouble still. And now, I hope most of you can see that. The spot is now, at least the size of a US $50. That's the best it can do, having gone through this tiny opening. The wave has been truncated in so many ways that that's all that's left. It's about the size of a $50, and it's got rings around it. We're called airy rings that have to do with how the constructive and destructive interference work or don't work. There are sort of rings of slightly constructive interference circling the main center. If I get smaller with the hole, the spot gets bigger. That's pretty big now. You okay with it? You can see it mostly? But it's getting dimmer. Can I go further? Let's see. Now that's the big hole again. This was the smallest hole I have up here. That's it. Okay? So this is an effect known as diffraction. When you send a wave through some sort of aperture or that blocks parts of the wave, you kill them off, and it can't, you change its ability to cause constructive and destructive interference, and typically it causes spreading of the wave. The overall structure expands. You can also think of this in terms of sort of Heisenberg uncertainty, if that's familiar to you at all. The idea that you can't simultaneously know where things in our quantum world are located exactly and in which direction they're traveling or how fast they're traveling exactly. You can't do them both. They're incompatible in part because of wave effects. And here's a wave effect too. You can't pin down the location of the laser beam super tightly by sending it through a narrow opening and know exactly which way it's heading, because it won't head purely in one direction. It will spread. And the more you pin it down in position, the more it spreads in sort of the equivalent of speed. All right? The consequences of this are many in our real world. For the laser beam that's used to read and write information on a CD, once you try when you try to get constructive interference on center and destructive interference everywhere else, you're limited. You want to make the beam travel through, essentially come from as big an initial structure as possible so that it can work with as many pieces of the wave as possible to create a tiny spot of constructive interference. So in this drawing up here, you don't want a narrow laser beam like this to start with going through the lens, because you won't be able to, you don't have enough pieces of the wave here, basically, to get constructive interference at a tiny spot here. Instead, you want to actually expand this laser beam to fill the entire lens. You want to make it wider to start with. It seems counterintuitive. You want to start with the widest laser beam you can and then focus it down, because now you're working with waves, with parts of the wave coming from this angle and all these other angles. You got a much richer palette to work with, and you can get a tinier spot. You're okay with that idea, I hope, mostly? So in a CD player, and I've got one up here, I'll plop it in here and show you the piece. Anyhow, document camera. There it is. I'm going to put it on that screen over there and try to remember to go back. Here, it's right here. You see that shiny thing right there? That is the lens. That is the lens that's taking a laser beam and focusing on a CD, which would be here if I put it in. You can see the tray in which it sits. The details here don't matter, apart from that lens is sitting in, it's got coils around it. They're electromagnetic coils, because it's positioned using the same features, the same behavior as a speaker. They run currents through those coils, and there are magnets around, and their forces then move the lens into just the right position. Why do you need just the right position? Because the lens is trying to hit this very tiny patch of symbols on the CD or DVD, and that takes exquisite control, particularly if you're moving this thing around. But the more important point here is they make the lens, that lens, okay, it's tiny here up on the screen, that's okay, but it is an extremely high quality lens. They blow up the laser beam to fill the whole lens. And then, so they're working with as many pieces of the wave as possible. That lens is very carefully engineered to pitch the tiniest little beam waves it possibly can onto the symbol inside the CD and observe it. Despite all that effort, now I'll stop doing this, they can't make the spot much smaller than the wavelength of light. They're limited by the wave nature of light. It's just, even if you're working with all the waves from all the angles, you can't do it. So if they want to illuminate smaller and smaller symbols, they need to use shorter and shorter wavelengths of light. So in the 80s, they could make little diode lasers in the infrared. You couldn't see the light, but it was there. And that was the light used in CDs. Later on, they could make red light. Laser diodes that would emit red light, they could use smaller symbols, and that's DVDs. And in recent years, they've been able to make blue laser diodes. And therefore, they can work with blue or ultraviolet light, and they can make smaller symbols still, and that's the Blu-ray discs. Is that okay with everybody? So this effect, this diffraction effect, and I can turn off this laser, where if you truncate a wave, you make it difficult to bring to a small spot. Believe it or not, that shows up in astronomy, in telescopes. Telescopes have gotten bigger and bigger for two reasons. One is because you collect more light, make the telescope huge. Beyond a certain size, you can't make refracting lenses worth anything. It's too hard. Getting the color corrections and stuff is too hard. So they go to mirrors as the optical elements. And you can create real images using mirrors. It works just fine. And so they use mirrors, and they collect lots of light with a great big huge mirror. But the other issue is diffraction. That when the wave has been traveling from that star, that tiny wee star over there, it's been traveling for 50 million years. And the wave, from each of the waves, they're thermal emissions. So they're lots of individual photons, each one for itself, but they have gotten very big with all that travel. And they retain wonderful information. The whole wave retains information of where it came from. So in principle, if you could collect the whole wave, you could find you could actually look at where on the star it came from, where that one light wave came from. But you can't do that because nobody makes a telescope that big. So instead, you make a telescope that's maybe as big as this room. I mean, they're sort of in that category at this point, I guess. And you try to collect a piece of the wave, but you want to collect as big a piece as possible, because when you truncate the wave by not collecting parts, you limit its ability to be focused tightly, and you can't make an image that really tells you exactly where the light came from. So the limits in astronomy, how much detail you can see, the limits are because of the wave nature of light. You just cannot resolve things that are really close together because you're truncating the light waves, and they will create spots that are bigger than you'd like, and therefore that overlap a little in space. The same way that spot, when I truncated the wave from the laser, it makes a spot that's this big. And if you have two such spots only separated like this, you can't resolve them anymore. You okay with that? So some of your money, your family's money is being spent on these giant telescopes. A key reason why they have to be so giant is to avoid diffraction limits and to try to get tiny spots and resolve details that you couldn't otherwise resolve. All right, so that's optical recording. Let me go on to, okay. Let me go on to optical communication. And the key point I want to talk about here is the transmission of information by way of light. And the basic background, of course, is it's usually digital transmission of information. It travels as symbols that are light. For example, blinking lights. Blinking light, you can use that to transmit Morse code or anything like that. So you can transfer information as light. If you do it in open air, you're subject to all the possibilities. So you can do it in open air. You can send, winking a flashlight at somebody. You've seen 1,000 spy movies where somebody's doing this, blink, 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 sending information. That's fine as long as it's not foggy, and then you're shot if you can't see the light. So what do? You put the light in an environment that's safe, that you can keep it under control. And the classic way to do that is to send the light inside a plastic or glass fiber. Well, why would the light travel through the fiber? Well, first off, the fiber better not be opaque. It's got to be transparent. How transparent? Exquisitely transparent. Because if you're going to send light through a piece of plastic or glass for a mile, it has so many opportunities to be absorbed that's got to be the clearest plastic or glass you ever saw. You've probably seen window glass from the edge on. It looks kind of greenish. Hopefully this is familiar to you guys. It's because ordinary window glass is just not that transparent. I mean, it's pretty transparent, but it's not wonderful. It's got a lot of impurities, mostly iron, that give it that green tint. And so that's not suitable for communication. You got to go cleaner. And so they've managed to make these unbelievably transparent glasses. Plastic has its limits. Finally, it's glass, and it's a quartz glass. It's a very high-tech glass, but it's transparent enough that that light can go through it for 100 miles with relatively little loss. But the other thing is, okay, so you send the light into a piece of glass. How do you keep it in the glass? Why doesn't it just leak out the sides? Light doesn't go dead straight. I mean, it does. The ray idea does, but the waves don't really go that straight. They have some spreading character. How do you trap it? And the way you trap it is by way of what's called total internal reflection. And the concept here is that if you've got glass or plastic here on the left, in which light travels slowly, and you have air over on the right side, in which light travels fast, when light tries to move from the high index material to the low index material, and remember, refractive index is a measure of how much light slows down in the material. So when you go from high index, that is travel slow, to low index, which is travel fast, it bends away from the perpendicular. Remember that idea? So if light was traveling totally along the perpendicular, it continues on the perpendicular. But if it was traveling at some angle to perpendicular, it bends away from the perpendicular. And as the angle at which it encounters that surface gets shallower and shallower, it bends more and more until finally it bends so far it doesn't get out at all. It bends beyond 90 degrees. I mean, the mathematics is sort of quirky. It gets to a 90-degree angle, and then the equation just changes character. It actually becomes complex, which is beyond what we need to talk about. But anyway, the reflection is perfect. It's not 99%, it's 100% to all the digits. No light, in principle, gets out beyond a very shallow distance beyond that surface. And this is true not only in the world of ray optics, but in wave optics. The wave just does not get out. And so, wow, you get a perfect reflection off that surface. If you then have the light traveling at a shallow angle through a cylinder of glass or plastic, it keeps bouncing off the surfaces as long as it hits them at shallow angles. And so you can get these situations where the light goes all the way through. Make it so you can see it. Can you see the lights coming out the other end? Is that okay? Ways in which I've got a whole slew of demonstrations like this. This is the basis for what are known as fiber optics. The light goes into the fiber from the end, and it skittles back and forth across the sides of the core, of the high index core, like plastic or glass, and never gets out because it reflects perfectly off the surfaces every time. In some cases where you can see that, I I can send this laser pointer in to this piece of plastic, and it will skittle back and forth across the walls and get all the way to the bottom. Oh, it's over here. I'm backwards. Can you see it? You're seeing it. It's arcing around here. It's coming down, and it's hitting the ground. Somewhere down here. You're seeing it only because the surface is so dirty that sometimes the light manages to go from plastic, not into air, but into crud. And once it gets into the crud, and the crud has an index of refraction similar to the plastic, so the transition isn't a problem. It doesn't do total internal reflection there. It leaks out. And once it gets into the crud is all randomly misshapen. The light hits it at a non-shallow angle and busts free. So that's why you're seeing it. Can you see the swirling light going all the way around the loop? You've seen these toys. These are fiber optics. The light is entering these fibers, skittling back and forth across them, and coming out the tips. And it's lots of fun. Is that so super useful? Who knows? These are more fibers. I'm going to send the light in over here, and you can see, because I'm using a laser, I can pick out which fiber I want the light to go into, and therefore which one it comes out. But it's traveling all the way through this. Having fun. All right. What else? Oh, this one. This is a sound. We've got an audio source here, which I'll start. I think. Yeah. And this is a transmitter. This transmits analog sound information. It's representing the sound as fluctuating intensity of the light. So it's not digital representation. It's analog, but it works anyway. Do I have this going here? So this is sending light that's varying in intensity. It's going through this fiber, this plastic fiber, over to here. And if I take the plastic fiber out, can you see the red light? That's the sound information coming along. And when I put it back in, okay? So clearly you can send information as a fiber, as a light in a fiber, and it will follow a fiber for a long way. By the time it gets here, it's bounced 1,000 times or 10,000 times, a whole slew. I can stop this. Okay. Any questions about the idea of the fiber optic then, the basic idea? Okay. One more demonstration is you can send light through a fiber of water. Is this going to work for me? What? It doesn't look right. Where's the light? No light. Can you see the light on my hand? So the light is there. That's better. This is a little ratty. It should do better. But the light is skittling back and forth inside the channel of water. All right, I'll stop. The details of how real fibers work. The fibers I've shown you so far, they're all pretty primitive. The transition between the fiber, they're all plastic actually, or water, and they go from the plastic or water to air. And they work nicely as long as that surface is completely clean. Nobody's bothering it. But they're pretty susceptible to junk. So what do? Well, don't expect air to be the low index surface off which the light reflects perfectly. Put a second surface there. Do it deliberately. And so sophisticated fiber optics, the ones that actually carry your internet or anything like that, they're made of approximately two different glasses. One of them is they're both exquisitely transparent. One of them is the core, and it has the high index of refraction. Light travels slowly in it. And the outside is the cladding, which is a second material. Light is not supposed to travel through the cladding. The point of the cladding is to make sure the light, when it hits the transition from one to the other, it reflects perfectly. So the cladding is outside there, and it protects the whole structure from the junk on the outside. Okay? So water, your hands, whatever's out there. So the light, in the simplest form, you send in light, and maybe you send it as a series of pulses. You're basically doing Morse code. You send the light in. Each time it comes in from the end, so it's traveling at a shallow angle when it encounters the interface between the core and the cladding, and it bounces by way of total internal reflection. It does it perfectly. Essentially no loss in this system. Back and forth, and it comes out at the end. That's the simplest type of fiber. It's just called a multimode fiber. Why is it multimode? It's because you've given the light opportunities to travel at different angles. It can bounce back and forth at a whole variety of angles according to the ray notion of light. In fact, in the wave notion of light, it's a little more limited, but still, it can bounce at many angles, and therefore, different parts of the light can travel different distances between entry and exit. And the consequence of that is that if you send pulses of light that are the symbols representing information, they go in as very short pulses, and they come out longer, because some parts of the pulse travel farther than others before they get out. You okay? Any questions at this point? Multimode fibers are great for local communication. This fiber, for example, is a multimode fiber. The light can go in at different angles and come out just fine, and you're not going to be able to transmit your gigabit internet or something like that. It'll work on these distances, but it won't work across town. So what do? Well, you can do a little better by not having a sharp interface between the core and the cladding. You use a gradient. They allow different chemicals to meander through the material, and they create a gradual transition from high index where the light travels slow on center to a low index where the light travels faster in the cladding. And the paths the light travel are a little curvy, and they get a narrower pulse. The travel time between all the possible paths through the core are not that different. You get a better better transmission fidelity. You get the pulse in and the pulse out are not that different. You can do better still, and this is where what all the long haul internet uses. And if you're sending information to Chicago or to Tokyo, this is what you use. They use what are called single mode fibers. In a single mode fiber, the core is extremely narrow, a few microns, that is a few millionths of a meter. It's tiny, you can't see it with your eye, thinner than a hair. And there is only one path through it for the wave. In the wave picture of light, which finally is the real picture, there is only one way the wave can travel through this core. It's a single mode of transmission. And the pulses in and the pulses out are, to this extent, identical. There is no one path. They all go the same distance. So you can transmit the most information per second through a single mode fiber. It's harder to work with because you have to get the laser beam into the end of this tiny fiber. So this is why it's all the big bucks, but that's the idea. Is it okay? Last details about this. So your internet is going as light waves. They come out of laser diodes primarily, I think, are able to blink on and off really fast if done properly. And this is a lot of engineering and development to get really fast so you can blink them on and off 50 billion times a second, that kind of stuff. And then you get exquisitely fast sensors that can watch the blinking on and off like that. You want to pack as much data as you want because somebody wants to stream the entire season of pick your favorite show tonight. They're binging, and they're in Europe, and they want to get it from the U.S., legal or otherwise. There's a lot of data going across, so you want to pack those little digital symbols as tightly as you possibly can. So they use single mode fibers. There's some things they got to deal with. First off, the fibers aren't perfectly transparent. They lose a little bit of intensity as the miles rack up. So if you want to talk to Paris, send your data to Paris, you actually have to build up extra light along the way. You can't send it all in at the beginning. You send it in as bright as you can at the beginning, but you got to amplify it en route. And they actually introduce into the fibers laser amplifiers every so often along the path between here and Europe. There are laser amplifiers in the fiber that take the light that's coming in and take this one giant wave and boost its intensity, make it brighter. So it's a whole technology to do that. That's one thing. Second thing is that I have neglected dispersion. Remember dispersion? The bluer light travels slower than redder light. Well, when you start pulsing the light, it's not a single frequency anymore. Just like with AM and FM modulation, when you start putting information on your radio wave, it's not a single frequency anymore. So these pulses actually have some bandwidth to them. They have a higher frequency end and a lower frequency end, and the lower frequency end travels a little faster than the higher frequency end. They get slurped out, and the pulse gets slurped out because of dispersion as it goes up 3,000 miles across the ocean, under the ocean. So they have to deal with that, and a way they deal with that is they find, for the core, they find the range and frequencies in which the dispersion is the weakest. And it's in the infrared, most fibers. So the long-haul fibers are carrying symbols as infrared light in around the dispersion minimum of these fibers. And that's most of the story of fibers. Anything else I want to say to this? Have I done all my demonstrations? I think so. So you okay with transmission of information by fibers, as light and fibers? Anything else? Something else is going through my head to talk about. Blah, 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 blah. Nope. Oh, yes, I did. I actually did want to, because I want next time not to talk just about this. I'm going to bring up something completely different really fast. And audio players would have been the next topic. I'm going to just lobotomize it. And I want to talk about a device, the key device in all computer stuff currently. It's called a MOSFET transistor, with the last letter, the T in that is transistor. It's called a metal oxide semiconductor field effect transistor. It starts essentially as two diodes. Remember diodes? Two p-n junctions. It's made of 3 pieces of semiconductor. In this case, it consists of a p-type semiconductor in the middle and 2 n-type semiconductors on the ends. When you touch that collection together, as with the p-n junction, electrons migrate across the boundary between those, across the junction. They leave the conduction levels of the n-type material and fill in the valence levels of the p-type material. So when you assemble this thing, you end up with a big depletion region where all the valence levels are filled and all the conduction levels are empty. This looks like a total disaster. It can't do anything. It can't conduct electricity. It's hopeless. The interesting thing, though, is this has a gate on it. It has an electrically chargeable surface separated by an insulator that can do things. You can put charge on this. And if you put positive charge on this surface, which is it's a conducting surface, so it's like a metal. If you put positive charge on there, it can attract electrons into the depletion region and begin to fill up the conduction levels. And when that happens, this thing goes from being a completely hopeless non-conductor to a conductor. And so here's a picture of it with conducting. You put positive charge in there, suddenly you can have electrons in the conduction levels attracted by the gate, and it conducts electricity. So this is a field effect. The electric field from the charge turns this thing on and off and everything in between. And it's exquisitely sensitive to charge, and that's the last thing I'll show you. I've got one up here, and we'll look at it from above on the side camera. There it is. It's this device here. And let me get some voltage here. Right now, it's not conducting electricity. I have 4 volts, that's 4 up here, between source and drain, it's called. The 2 ends, these are source and drain, it doesn't matter. And there's the gate electrode doing nothing. If I put positive charge on that gate electrode, it will become, this guy will become a conductor, and it won't have a voltage drop anymore. Well, how am I going to put positive charge on it? Oh my gosh, what am I going to do? I'm going to take positive charge off the positive wire here and put it on with my finger. Not very compelling. Can I get this better? Oh, Here, you can see the current flow. That's probably a better indication. Current on. Oh, this is not very compelling at all. Give it one more second. At the beginning of next time, I'll do it better. The point I'm trying to make here, which I'm not getting because I'm probably screwing it up, is the charge that goes through my hands is enough to turn this thing on and off. So tiny amounts of electric charge can control the flow of current across some powerful thing. This is the basis of all your computer stuff, all your modern electronics. They're all filled with these field effect transistors. And digital memory, the active memory in your computer, it's all based on this